Hi everybody, so lesson 3.3, we're going to, now that we've talked about quadratic equations, we're going to talk about some other um, types of functions and then talk about their associated equations. So this lesson is going to talk about logarithms, okay? We're going to talk about the basic aspects of them as well as some properties, those properties being ways you can manipulate them in equations to solve for certain variables. So a logarithm is what I call the opposite of when you're looking at an exponent. Okay, so for an exponent, if we had 2 to the exponent 6, that's equal to 64. Okay, so what that means is 2 times 2, 6 times, would give you 64. So that's why the exponent here is 6. A logarithm is trying to solve directly for this exponent. Okay, so when you see the log function, it's on your calculator, you might see it written as log. It has a base, okay, the base being whatever number you're going to multiply out multiple times. And the number you put in the logarithm, if you were to put it in your calculator, would be the power. In other words, the final solution. So you're starting with two numbers, in this case, 2 and 64. And you want to see how many times you have to multiply 2 by itself to get to 64. In this case, the resulting number that would come out of your calculator would be 6. So you'd have to multiply 2 by itself 6 times to obtain 64. Okay? So while the exponential equation looks at the final solution, which is called the power, the logarithm looks at the exponent. Okay? So the solution coming out of it is the exponent. So if you want the actual term for it, a logarithm is defined as the exponent to which a base must be raised to produce a given number. Okay? So some examples of these. This is all the same number, 64. But depending on the number you use, you have a different exponent. If your base is 2, you have to multiply 2 by itself 6 times to obtain 64. So the logarithm with base 2 of 64 would give you 6. If you use the number 4, you only have to multiply 4 by itself 3 times to get 64. So your logarithm of base 4 for the same number, 64, would give you a different exponent. It would give you 3. And if you use the number 8, well, 8 squared is 64. So that means the exponent for that one is only 2. So that means if you had a logarithm with the base of 8 and of the number 64, you would get the answer of 2. So depending on what your base is, you get a different number. Obviously, the smaller the base, the more you'd have to multiply it out to get the same kind of large number. Okay? So just to look at some examples of these. So what I want you to keep in mind here is all of these have different bases. You'll see 2, 4, 8, 10. We're going to talk about what the common base is for logarithms in the next slide. Okay, it's actually base 10, and we'll talk about what that means. But first of all, let's look at a few examples. So for A, the logarithm, the base is 2, the final answer is 8. So how many times do you have to multiply 2 out to get to 8? Well, 2 times 2 is 4. That's not it. Times 2 is 8. So that's 3 times, which means your final answer would be 3. Okay? For question B, our base is 8 and our final number is 8. Okay, they're the same number. So you don't have to multiply it out. The answer would just be 1, right? Because 8 to the exponent 1 is 8. Okay? Part C, the log of the base 2 and 16. Okay, again, what exponent, 2 to what exponent would give you 16? We're trying to figure out what this exponent is. So again, you want to think of it this way, 2 times 2 is 4, times 2 is 8, still don't have it, times 2 is 16. That's 4 times, right? So that's the same as writing 2 to the exponent 4. So what we're solving for, remember, is this exponent, which means our answer for this would be 4. Part D, logarithm and the base is 4 and the number is 16. So 4 times 4 is simply 16. You can also write that as 4 to the exponent 2. So your answer would simply be 2. Okay, I wrote this in green. I'll switch back to red. For example E, you have the log of the base of 16 and the number is 16. Remember, that's the same as this example here, right? You don't have to multiply it by itself, okay? So the answer is simply 1 because 16 to the exponent 1 is 16. For F, okay, we have the log, the base of 2, and the answer is 1. So 2 to what exponent here would equal 1? Well, remember, any number to the exponent 0 is 1. So that means that this answer must be 0 because 2 to the exponent 0 is 1. But there's no other solution to that that would give you 1. Okay? And it doesn't matter if it's 2 to the exponent 0, 4 to the exponent 0, 1,000 to the exponent 0. They're always 1. Okay? That's an important property to know. For G, we have the log of 2. And the number is 1/2, okay? This one is a little bit different. Remember, we can write something that's in the denominator and move it to the numerator if we change the exponent. So what that means is this is the same as writing it as log of base 2, and this would be 2 to the negative 1. I've moved the 2 to the numerator. Okay, remember, if it's just written as 2, that's the same as 2 to the exponent 1. So when you move it to the numerator, you get 2 to the exponent negative 1. Okay, well, you kind of have your answer here. So what exponent do you have to raise 2 to get 2 to the negative 1? It's the same exponent that's already written here. Okay, so the answer to this is simply negative 1. Okay, for H, log of base 10 and the number is 100. Again, following the same path. We have 10 to some exponent is equal to 100. Well, 10 times 10 is equal to 100. So that means that this can be written as 10 squared, so our answer must be 2. For I, the log again of base 10 for 1,000. So again, we have 10 to some exponent x has to equal 1,000. So 10 times 10 is 100, times 10 is 1,000. So that can be written as 10 to the exponent 3. So our answer in this case must be 3. J is our last example, okay? And it's the log base 10 of 1 divided by 100. In this case, we're going to have to do a couple steps here, okay? First thing is just like we did in example H here. Okay, so remembering that we move this to move to the numerator. But before we do that, we know from example H that 100 is simply 10 squared, right? So we can rewrite this, well, that's a bad O, as log base of 10 of 1 divided by 10 squared. Now, following the same path, if we want to move that from the denominator to the numerator, this becomes the log of base 10 of 10 to the negative exponent, or negative 2. So now we're asking ourselves, what do we have to raise the exponent 10 to get to 10 to the negative 2? Well, again, the exponent is here. That is what we're trying to find. So the answer in this case would simply be negative 2. Okay, so all of these are different examples using different bases. Okay, but they all follow that same premise. We're trying to figure out what that exponent is. So you can actually remember when I was finding the logarithm, I was converting it to an exponential form. Okay, the base or whatever that number is written to an exponent. So you can actually work those kind of together. You have something like 8 equals 2 to the exponent 3. You can write that in logarithmic form. Okay, we know the exponent is 3. So the final answer to that would be 3. And what that equals is the log of the base of this number. The base here is 2. and the final answer, which is the power, is 8. So you can write these interchangeably. Basically what I'm saying is, if you have some function y equals some number a to the exponent x, you can write that as x, or the exponent, is equal to the log of the base, which is a, and the number that you're putting in for the log is y, the final answer that would come out. Okay? So as an example here, if 25 is equal to 5 squared, we can write that as the exponent, 2, is equal to the log of the base, 5, of the number 25. Okay, so the power. If we have 81 is 3 to the exponent 4, which it is, then that means the exponent 4 is equal to the log of the base, okay, base 3, and whenever you put in your calculator is the final answer, which is 81. Okay? So let's look at a few additional examples. I'm going to give you the value, and I'm going to give you the base. Okay? We need to figure out what the exponent is, and then I want to write it in both exponential and logarithmic form. Okay? So first we have the value is 32 and the base is 2. So if the base is 2, that means we have 2 to some exponent x is equal to 32. Okay? Again, in these ones I'm not going to give you one that's a fancy decimal or anything. So we're going to be able to figure this out just using math. So 2 times 2 is 4. Doesn't work. Times 2 is 8. Still not big enough. Times 2 is 16. We're getting closer. Times 2 is 32. So we count these up, we get 5 2's. So that means that 2 to the exponent 5 must be equal to 32. So in exponential form, we'd have 2 to the exponent 5 equals 32. And if you switch that to logarithmic form, your exponent, 5, must be equal to the log of your base, which is 2, and times your number, 32. Okay? For the second example, we have the value of 256 and the base of 4. So that means 4 to some exponent x has to equal 256. So 4 times 4 is 16. Times 4 is 64. Still not there. Times 4, you can do this in your calculator, or if you can do it in your head, great. So 64 times 4 is 256. So we've arrived at it. So in other words, 4 to the exponent 4 must be 256. So in exponential form, 4 to the exponent 4 is equal to 256. In logarithmic form, the exponent 4 must be equal to the log of the base of 4 of the final number, 256. Okay? Last example, the value is 6, the base is 36. Okay? So this one is a little bit different. You have 36 to the exponent x has to equal 6. How do we work backwards? Okay, before I've multiplied all of these together. But in this case, how do we work backwards? Well, I know, stopping and thinking about this, the square root of 36 is 6. Okay, drawing back to our previous unit where we talked about fractional exponents, remember, if we had the square root of some value, a, that was the same as a raised to the exponent 1 over 2, okay? Or it was the order of the root, okay? So if we had a third order root of a, you would write that as a to the exponent 1 divided by the order of the root, 3. So the reason this is half here is because for the square root, the order of the root is 2. We just often omit it. So knowing that, we know that the exponent here must be 1/2 because the square root of 36 is 6. So we have 36 to the 1/2 is equal to 6. And if you were to write that, our exponent, 1/2, is equal to the log base of 36 of the number 6. Okay? So it's pretty rare to see it this way. Usually the base is a smaller number. than the number you're taking the logarithm of, so the 256 or the 32, but it doesn't always happen that way, okay? So knowing fractional exponents from our last unit will also help you in solving these. So now that we've seen these, I want to talk about what's called a common logarithm. So your calculator has a log button. That log button works on a common base. That base is 10. Okay, so anytime you use your calculator, it's going to do the logarithm of 10. Unless you have a more expensive version, you can't switch that base from 10 to another one. Okay, so you can't switch it to base 8 or to base 4. Okay, so to do those calculations, most of the time when we do them in class, you're going to leave them in their logarithmic form. Okay, but often what you see is if you look at your calculator, it just says log. It doesn't show a base, it doesn't show anything else, and that's because 10 is the universally understood common logarithm. So we often omit that, all right? So what we see here is you could write it as log of base 10 of a number, but often instead we omit the base 10. So what we show is instead log of 100. So if no base is shown, it's understood that that base is actually 10. Okay, so that is the common one used. It's just like when we had the square root of a number. You just showed the square root symbol. You didn't show the square root with the order of the root being 2. And your calculator doesn't show it like that either. And that's because it's kind of the universal one, the square root, right? You all know what the square root is. You may not have heard of the cube root or the fourth root or the fifth root, but you know what the square root is. The same thing happens with the logarithm function. Okay, so anytime you see a question where it just says log of 106, what that actually means is the log base of 10 of the value of 106. Okay, and the same thing happens when you place that number in your calculator. So if you place that in your calculator and you type log 106, okay, you would get your answer. In this case, it's not going to be a perfect exponent. It's actually 2.025. Okay. So looking at some examples of this, all right, so let's say we have the log of 10, okay? So the log of 10 is equal to 1, and that's because pretending there's a base of 10 here, 10 to the exponent 1 would give you this power here of 10, okay? The log of 0.1 is equal to negative 1, okay? Again, these are all numbers that you would likely place in your calculator, and that's because 0.1 is equal actually to 1 over 10. Okay, I don't expect you to do that piece, all right? But what you see here is they all rely on the base 10. Then you can have an example like I just showed you, the log of 72. Remember I showed you log of 106. And you're not going to get an exact number, okay? These are numbers you're going to put in your calculator. And the reason for that is if you were to take 10 to the exponent of the number your calculator gave out, you would arrive back at the original number that you started with, okay? So some common values here. Again, each of these you can use with your calculator by simply typing in for the first one, log of 1,000. Okay, you would arrive at 3. So I don't expect you to necessarily do these ones by hand. Now I kind of want you to get used to using your calculator. It's great to show you logarithms of other bases, but when it comes to your calculator, these are going to be the only ones you're going to be able to use it for. Example B, the log of 1 million. Okay, so that simply is 6. That's just 10 to the exponent 6 is 1 million. The log of 0.0001, in that case, is negative 4. And that's because 1 divided by 10 to the exponent 4 would give you that answer. Okay, again, whenever you see it as a decimal or a number that'd be smaller than the logarithm, it's normally going to be either 1 divided by that base 10 to an exponent or a square root. Okay. For D, the log of the number 1, okay, so that's going to be 0 because 10 to the exponent 0 would give you 1, okay, the number that you started with here. And lastly, log of 147.2, again, a number that you're not going to be able to do that in your head to figure out the exponent. But you can do that in your calculator. And you would arrive at 2.16. You can round it to 2.168. I showed it down here with all of the decimals. But either way, round it to a reasonable number of decimals. Okay, so like I said, most logarithms you can't actually put in most calculators. Okay, you can only put it to the base of 10. So what we have to rely on is logarithmic relationships. And that's not only to be able to solve for these when they have a different base, it's also if we have a variable in the equation that's in the logarithmic function, an x or a y or something like that. So we can use relationships. These are very similar, except working kind of backwards to the rules of exponents you saw in the last unit. So I'm going to start with, if you have two terms multiplied together, let's say you have the log, okay, and I write base b because that could be any base. Doesn't matter if it's base 10, which is what our common one is, or if it's 2 or 4 or whatever it is, doesn't matter, okay? And you have two items multiplied together, x and y. Let's say it's 3x. You can actually write that as the logarithms of each separately, but added together. So this would actually be the log of x plus the log of y. Or in other words, using our example, log to the base b of 3 plus log to the base b of x. Okay, so you can separate them out, making sure you add them together. If they are divided, then you have to subtract one from the other, okay? Making sure the one in the denominator is subtracted from the one in the numerator, okay? It doesn't work backwards. You'll get the opposite solution. So if we worked the same way and we had 3 over x, it would be the log of b of 3 minus the log base b of x, okay? So the same thing, just subtracted. Our last solution is if you have the log of something raised to an exponent. So let's say you had 2 to the exponent 4. You can actually move that exponent behind the log function and multiply it out. So it becomes the exponent times the log of just the function x, or the base x. So in this case, that would be equal to 4 times the log of 2. Okay? So you're simply moving that exponent out. Again, all of these will be used if in case you have to solve for a variable, usually solving for x. Okay, so now let's finish off our lecture by looking at some examples using these logarithm relationships. So first example is expand the log of the base 2 of 3xy using logarithm relationships. So this one you see we have 3 terms multiplied together. So remember, we can write these instead of the log of each of them individually added together. So what this becomes is the log base 2 of 3xy. It's equal to the log of each of these components. You see 3 components, 3, x, and y. It's to each of these individually, the log of them, so log base 2 of 3 added together, plus the log base 2 of x, plus the log of base 2 of y. Okay, so it's simply taking that starting piece and breaking them out. So again, it's useful because now you have x by itself or you have y by itself, depending on which one you're looking at solving. Okay. Our second example, it's the log of a to the exponent 5 times 2b, again using logarithmic relationships. So we have 3 items, again, added and multiplied together. A to the exponent 5, 2, and b. So we can start by breaking all these out. So the log, okay, and again I have log here. That's understood when there's no base that it's base 10. So we don't have to write base 10, we just know it is. So we have the log of a to the exponent 5 times 2b is equal to the log of the first term, a to the exponent 5, plus the log of the second term, which is 2, plus the log of the third term, which is b. Now, we're not quite done yet in this case. We have an exponent here, so we can simplify this further by moving that exponent outside of the log function. So that becomes 5 times the log of just a, now, plus the log of 2 plus the log of b. Okay? Again, these are just expanding them out. In our next lesson, we're going to look at how to actually use that to solve for each of these. Okay? Our next example is expand the log of 2x divided by 3 to the exponent 5 using logarithm relationships. So we see there's several parts to this. In the numerator, we have 2 pieces multiplied out. Then we have in the denominator something raised to an exponent. Okay, so there's 3 parts to this. The first part is going to be expanding out the 2 in the numerator and then subtracting that 1 in the denominator. So we're using all 3 of the rules here you're going to see. So starting off, we have the log of 2x over 3 to the exponent 5. That's equal to the log of the first term in the numerator, 2, plus the log of the second term in the numerator, which is x. And then remember, when they're divided by each other, you subtract it. So that's minus the log of the remaining term, 3 to the exponent 5. So now you can see again, we still have one more step to do because we have an exponent here. So we can move that exponent in behind the log function. So that becomes the log base 2 plus the log of x minus 5 times the log of 3. Okay? And our last example, okay? Expand the log of 2 plus 1 over x divided by x times y cubed. So there's actually only 3 terms here. The 2 plus 1 over x, remember, it's only if they're multiplied or divided by each other. So this piece in the numerator has to stay as 2 plus 1 over x. All right? It can't actually be broken out into log of 2 and log of 1 over x. So if we write this out, we get the log of 2 plus 1 over x divided by x times y cubed. So we start with the log of the function in the numerator, which is 2 plus 1 over x. Then we subtract the functions in the denominator, so minus the log of x minus the log of y cubed. So now our last step, you can see we have an exponent here that we can move in behind. So is this equal to the log of 2 plus 1 over x minus the log of x minus 3 times the log of y. Okay. Now, some of you might be asking, why can't we simplify this any further? The only thing you technically could simplify that's further is you could combine all of these into one fraction and then use the rules again to subtract those functions, the one in the numerator from the one in the denominator. But in this case, it doesn't seem like a useful step because we're not actually going to solve for the function x. Okay? All right, so that was all I had for this lesson. Again, I'm giving you the odd numbered problems here because most of them in the textbook, the solutions are there. If you have any questions, please send me an email. Again, with these, practice makes perfect for them. It makes you become a lot faster at doing them, which is going to help you when we get to our test. Okay, thanks everybody.